Hey, how's it going everyone? My name is Dan the Tutor and we're back with another lesson. I wanted to continue with some example problems with continuity at a point, specifically with piecewise functions, because those are definitely the trickiest examples. So let's just do a couple more example problems with that and really kind of have it down. So here's an example. I want to know, is f of x equals piecewise function? In the top portion, we're going to have x squared minus x. And specifically, we're looking at the point when x is greater than 2. And then in the bottom portion, we're going to have negative x plus 4. And that's when x is going to be less than or equal to 2. So it's important to understand that the x greater than 2 part, that's going to be coming in from the right. And the x less than or equal to 2, that's going to be the left. So that's important to think about when we're talking about the second step for continuity, which is evaluating the limit from both sides. So now the first step when it comes to computing continuity is we first need to prove that the value f of 2 exists. So what is the value f of 2? If I were to plug in 2 into this piecewise function, would I be looking at the top or the bottom? It's going to be the bottom because we have the less than or equal to symbol. So in that case, we have f of 2 is equal to negative 2 plus 4 because we're plugging into the bottom. And so what we get there is just 2. So our value exists. We have the value of 2. Now we're going to find the limit. So step 2 involves finding the limit as x approaches 2 of f of x. And since we have a piecewise function, since we have a left side and a right side, what we essentially need to do is find the limit from both sides. So the limit as x approaches 2 from the left f of x. Remember, minus sign means left, and left means we're plugging into the bottom function since less than or equal to 2 is from the left. So that's going to be negative 2 plus 4. It's going to be the same thing we got earlier, and it's just going to be positive 2. And now we're going to do the same thing for the right side. The limit as x approaches 2 from the right f of x. And remember, the right is going to be using that top function, x squared minus x. So for that limit, we can just plug in and use direct substitution since there's no domain errors. And we get 2 squared minus 2, which is going to be 4 minus 2, which is just going to be 2. And since these two numbers equal each other, then that means the limit as x approaches 2 f of x is just equal to 2. And since that limit exists, I'm going to put a check mark. We are good to go. And now the final check, step 3, is that we need to prove that f of 2 is equal to the limit as x approaches 2 of f of x. And since the value of f of 2 was just 2, and the limit as x approaches 2 was also 2, with those two equal each other, we get the check marks. It is continuous. At x equals 2. And that's the answer to our question. And that's how we're going to solve these piecewise function problems, especially for continuity at a point. It's a lot of work, it's a lot of steps, but each one is essential and it's going to help your understanding for piecewise functions and limits moving forward. So it's good practice in the very least. Let's look at one more example. Is f of x equals, I'll say negative x plus 2 when x is greater than 3. When x equals 3, I'll give a value of 0. And then when x is less than 3, I'm going to say it has a value of negative 4 plus x. Okay, so now this piecewise function has 3 possible values, and we want to know, is f of x continuous? Is this continuous at x equals 3? Okay, so the steps don't change. The first step is we need to know what the value is at f of 3. And if we were to plug in 3 into this piecewise function, are we going to use the top, middle, or bottom? It's going to be the middle, and that's because that's the one with the equal sign. And so we know the value is 0 at f of 3. Now let's find step 2, which is the limit from both sides. So the limit as x approaches 3, f of x is equal to what? Well, first we need to find it from the left or the right. We'll start with the left. Limit as x approaches 3 from the left, f of x is equal to, which function are we plugging into here? If it's from the left, is it going to be greater than, less than, or equal to? It's going to be the less than sign. And so it's going to be negative 4 plus x. So we can use direct substitution. Negative 4 plus x, which is 3. And so what we get there is just negative 1. Now, same thing. Limit as x approaches 3 from the right f of x. That's going to equal, well, if we're talking about the right, that's going to be the top equation because it's greater than symbol. And so it's negative x plus 2. So negative x, which is 3, plus 2. That's going to give us negative 1 as well. And notice, once again, these two values are equal to each other, which means our overall limit as x approaches 3 is also going to be negative 1. Now, it's not done yet. We can't forget step 3 because step 3 says, hey, does my value, f of 3, equal my limit as x approaches 3? Well, if my actual value at 3, I actually plug in 3, I got 0, and my limit was negative 1, then these are most certainly not equal, and I fail my third check, and the function, therefore, is not continuous. It's not continuous. And that's why, because it didn't satisfy all 3 checks. And if you want to think about what case just happened here, like why it wasn't continuous from like a graphical standpoint, let me show you. So from a graphical standpoint, what we have going on here is we have some graph, and things get a little wonky at x equals 3. From the left and the right side, it's approaching the same number. It's approaching, negative 1, and there's a hole in the graph, and they have different shapes or whatever. But the actual value is 0. And so what that looks like in terms of the piecewise function we were just dealing with, it has one shape from the left, one shape from the right. They're approaching the same value, right? Like the limit exists. It's approaching the same value, that negative 1. But the actual value, the closed circle, is a dot. And if we remember what continuity is, continuity says, can we draw this without lifting our pencil? And if I have to lift my pencil at that dot, then we most certainly do not have continuity. And so that's what's going on here. I think this is a good example. And yeah, that's pretty much it. My name is Dan the Tutor. Thank you for watching, and I'll see you next time. Bye-bye.